Welcome to EFIWE, excellence without stress.
Hi dearest EFIWE, we are back again on this our excellence without stress journey, and today we are going to take another topic, which is capacitor. So today we are going to learn about capacitors and capacitance. What is a capacitor? A capacitor is a two-terminal electrical device that can store energy in the form of an electric charge. A capacitor is a two-terminal electrical device that can store energy in the form of an electrical charge. It consists of two electrical conductors. That are separated by a distance. You can see the distance. They are separated by a distance. The space between the conductors may be filled by a vacuum or with an insulating material known as a dielectric. The ability of the capacitor to store charges is known as capacitance. So a capacitor is the device that can store energy. This is a capacitor, but that ability of the capacitor to store charges is known as capacitance. So let's take that again. The ability of the capacitor to store charges is known as capacitance, but the device itself is called a capacitor. Capacitors store charge energy by holding apart pairs of positive charges. We know the positive charges, like we know the pair of opposite charges, rather we know the opposite charges, the positive and the negative. The simplest design for a capacitor is a parallel plate, which consists of two metal plates with a gap between them. But different types of capacitors are manufactured in many forms, styles, lengths, girths, and materials. Types of capacitors. From our picture here, we can see the different types of capacitors. We have the fixed capacitor, mica capacitor, paper capacitor, film capacitor, ceramic capacitor, electrolytic capacitor, variable capacitor, and polyester. All these capacitors are different by what separates them. The film capacitor are the ones that use plastic film as the dielectric. Can you see that now? This is the film capacitors. They use what? The plastic film as the dielectric. They are available in nearly any value and voltage up to 1500 volts. They range from 10% to 0.01% in any tolerance. Additionally, film condensers arrive in the combination of shapes and case styles. There are two types of film condensers. We have the radial type lead and the axial type lead. So this is the film capacitor. So you see the dielectric is a plastic film. So the next one is the ceramic capacitors. Ceramic capacitors are the ones, this is ceramic capacitors are the ones that use ceramic as a dielectric material. So that is just simple ways of defining these types of capacitors. So the ceramic capacitors are the ones that use ceramic as the dielectric material. It is used in high frequency circuits such as audio to RF, that's radio frequency. In ceramic capacitors, one can develop both high capacitance and low capacitance by altering the thickness of the ceramic disc. So if we alter the thickness of this ceramic disc, we can develop both the high capacitance and low capacitance. You know what capacitance is? Is the ability of that device, which is a capacitor, to store what? Electric charges. So then we have the electrolytic capacitor. This is it, the electrolytic capacitors, and we know what's that. So the electrolytic capacitors are the ones that use the oxide layer as the dielectric materials. It has a wide tolerance capacity. There are mainly two types of electrolytic capacitors, the tantalum and the aluminum. They are available with working voltages of up to approximately 500 volts, but the maximum capacitance values are not available at high voltage, and higher temperature units are available but are rare. And this also is another type of capacitor, the variable capacitor. This is it. Variable capacitors mostly use air as the dielectric medium. A variable capacitor is one whose capacitance can be mechanically adjusted several times. For example, this form of the capacitor is used to set the resonance frequency in LC circuits, to change the radio to match the impedance in antenna tuner device. So you can see it now. So we can alter this type of capacitor, and that is why it's called the variable capacitor. How does a capacitor work? So look at it now. For demonstration, let's consider the most basic structure of a capacitor, the parallel plates. These are the two parallel plates you can see from here, plate 1 and plate 2, and there is a dielectric between it, separating the two plates. So for a demonstration, let's consider the most basic structure of a capacitor. The parallel plate capacitor It consists of two parallel plates. Yes, this is the positive part and this is negative part. So you can notice that this is a cell, a battery are connected to it. The positive side of the cell is connected to to plate 1, and the negative side is connected to plate 2. So positive charges are stored in plate 1, negative charges are stored in plate 2. So let's read. For demonstration, let's consider the most basic structure of a capacitor. The parallel plate capacitor, it consists of two parallel plates separated by a dielectric. When we connect a DC voltage across, this is a DC voltage across the capacitor, one of the plates is connected to the positive. You can see the plate, this plate is connected to the positive and the other to the negative. You can see that when the potential of the battery is applied across the capacitor, plate 1 becomes what? Positive charge, because it was connected to the positive terminal. Then plate 2 becomes negative because it was connected to the negative terminal of the battery. The current tries to flow through the capacitor. You know, ideally this current is supposed to flow, but because of this dielectric, this separation, it will just stop here and it will stop here. So the current tries to flow through the capacitor at the steady state condition from its positive plate to its negative plate, but it cannot flow. Why? Due to the separation of the plate with an what? Insulating material. So this is how the capacitor works. This is how it is able to store charges, because ideally it collected the positive charge. This plate 1 is positively charged, plate 2 is negatively charged. Yeah, but instead of the current to continue flowing, there is a separation. This is an insulator called the dielectric. So this separation is what prevents the positive going into the negative part of the plate. So an electric field appears across the capacitor. The positive plate accumulates positive charge, yes, and the negative plate accumulates negative charges from the battery. After a point, the capacitor holds the maximum amount of charge. That is, it holds the maximum amount of charge as per its capacitance with respect to this voltage. This time span is called the charging time of the capacitor. This time span is called the charging time of the capacitor. When the battery is removed from the capacitor, the two plates hold a negative and a positive charge for a certain time. Thus, the capacitor acts as a source of what? Electric. Therefore, there is short time. This capacitor would, this plate, the plate 1, will hold the positive charge. Plate 2 will hold the what? Negative charge. So, if these plates are connected to a load, this is the load, the current then flows. You can see the direction. The current then flows. Current flows to the load from plate 1 to what? To plate 2 until all the charges are dissipated from the plate. This time span is known as the discharging time of the capacitor. The time the charges are loaded into the plate is known as the charging time, and when the charges are sent to the load is known as the what? The discharging time of the capacitor. It's known as the discharging time of the capacitor. Concept of capacitance. We already explain to ourselves that capacitance is that ability of capacitor to do what? To store charges. So what are the concepts that would be meeting when we talk about capacitance? The ability of the capacitor to store charges. The conducting plates have some charges, Q1 and what? Q2. And as we saw, Q1 can be positive and Q2 what? Negative. Usually, if one plate has positive Q, usually if one plate has positive charge Q, the other has what? The negative charge. So the electric field in the region between the plates depends on the charge given to the conducting plates. We also know that potential difference V is directly proportional to the electric field. Hence, we can say Q is equals to what? CV. You remember, Q is directly proportional. The charge is directly proportional to the what? The potential difference. So Q is equals to what? CV. And C can now be equals to Q over V. I'm sure we understand how we got this. Charge is equals to C multiplied by V. This C is a constant. So the constant of proportionality is known as the capacitance of the capacitor. You know, when we say this part now, is as if I'm saying Q is directly proportional to V. Let's go to our board to try to write that. Then we introduce the constant. We introduce the constant. Q is directly proportional to V, and Q is equals to what? CV. Q is equals to CV. And if we make C the subject of formula, so C is going to be equals to what? Q what? Over V. C will be equals to Q over V. and that was how we got our C, and this is the capacitance of the capacitor. So the capacitance of a capacitor, which is a constant of proportionality, is what Q, which is the charge divided by the what potential difference, because our Q is directly proportional to V. So changing the proportionality sign to equals to, we're going to introduce a constant, and that constant is C. So C is a constant of proportionality known as the capacitance. That's the ability of this capacitor to store charges. Capacitance is a ratio of the change in the electric charge of a system to the corresponding change in its potential. So that's the ratio. You can see it now. Capacitance is the ratio of the change in the electric charge. This is the charge of the system to the corresponding change in its electric potential. The capacitance of any capacitor can be either fixed or variable depending on its usage. From the equation, it may seem that C depends on the charge and voltage. Actually, it depends on the shape and size of the capacitor, and also on the insulator used between the conducting plates. You know, we talked about different insulators, the film, the ceramic, and so many other types of capacitors. So energy stored in a capacitor. Once the opposite charges have been placed on either side of the electric plate capacitor, the charges can be used to work by allowing them to move towards each other through a circuit. The equation gives the total energy that can be extracted from a fully charged capacitor. So the energy in a capacitor is given as 1/2 CV squared. That's 1/2 CV squared, and that is how to get the energy stored in a capacitor. Capacitor functions a lot like rechargeable batteries. The main difference between a capacitor and a battery lies in the technique they employ to store energy. Unlike batteries, the capacitor's ability to store energy doesn't come from chemical reactions, but from the physical design that allows it to hold negative and positive charges apart, and that's by putting the dielectric between the two plates, and that is the ability that the capacitor has. Standard unit of capacitance. The basic unit of capacitance is the farad. Yes, the capacitance is measured in farad, but farad is large unit for practical tasks. Hence, capacitance is usually measured in subunit of farad, such as the microfarad. Most times, this is the unit we use for the capacitance, micro or the picofarad. So 1 microfarad, 1 millifarad is times 10⁻⁻3, microfarad is times 10⁻⁻6, nanofarad is -9, and the picofarad is -10 farads. And this is the capacitance of a parallel plate. You can see that this one is one that is going to hold the positive charge. This one is the negative charge, and this is the distance, the dielectric, the separation. So this is the parallel plate capacitor. So now we are going to capacitance of a parallel plate capacitor. The parallel plate capacitor, as shown in the figure, has two identical conducting plates. I'm sure we can remember that two plates, plate 1 and plate 2, each having a surface area A and separated by a distance D. Yes, there was a separation, and that separation is where the dielectric material is kept. When voltage V is applied to the plate, it stores charge Q. The force between charges increases with charge values and decreases with the distance between them. So also, the bigger the area of the plates, the more charge they can store. Let's not forget that is the capacitance of a capacitor is directly proportional to the area. A bigger area means more capacitance, like more ability of the capacitor to do what? To store charges. So capacitance is directly proportional to the area. Similarly, the closer the plates are, the greater the attraction of the opposite charges on them. So therefore, C is greater for a smaller d. So what is this saying? It's telling us that the capacitance of a capacitor is inversely proportional to the distance. So the smaller, look at this part now, the smaller the distance between these plates, the more the capacitance ability, the more the ability of the capacitor to store charges. That is what it's trying to say. And the area, it is directly proportional to the area, directly proportional. The bigger the area of the plates, the bigger the area of these plates, the bigger the area of the dielectric of the plates, greater the capacitance of the capacitor. So let's try to get another equation for the capacitance of a capacitor. You know, we've already accepted that the capacitance of a capacitor is the charge divided by the the potential difference. That's the ratio of the charge and the potential difference. So remember that we have that E is equals to what? Electric potential difference divided by the distance between what? The two plates. E is equals to electric potential difference divided by the distance between the two plates. Then we have E is equals to V over D, and making V the subject of formula, we have our what? ED. We have our ED. So V also, from our previous classes, we established that V is equals to sigma multiplied by the distance divided by epsilon naught. We've established this. Sigma multiplied by D divided by what? Epsilon naught. So also, we know that our C is equals to Q over V. Don't worry, we'll go to our board to quickly explain. We'll go to our board to explain. So C is equals to Q over V. What are we then going to do? We are going to put this value of V into this equation, and putting that, we are going to get this, that our C then is Q multiplied by the epsilon naught divided by sigma multiplied by what? D multiplied by D. So let's go to our board quickly to see what we are talking about. So look at it now. From the board, we already have that our V is equals to sigma. Let's write that very straight. Control Z. We have that our V is equals to what? Sigma D divided by what? Epsilon naught, right? And our C is equals to what? Q divided by V. Our C is equals to Q over V. So now, it's just as if I'm saying C is equals to Q divided by what? Divided by V. Then what will I now do? Then Q divided by putting that value of V we have, which was sigma multiplied by D divided by epsilon naught. So putting it here now, what are we going to do? We're going to have to change this division sign to multiplication. So it's going to be Q times epsilon naught divided by sigma what? D. So our C then can now be what? Q, epsilon naught, then sigma, and what? And D. So we've established, but this Q over sigma is a value. So C can also be what? C is equals to A, because Q over sigma is equals to area. Charge over the sigma is equals to what? Is equals to area. So it's A divided by what? That's going to be A epsilon naught over what? Over D. And this is another formula for our C, our capacitance of the capacitor. So let's go to our board, our slide, to check it again. So you can see now that we have that our capacitance of capacitor is now equal to this. This is epsilon naught is the permittivity of free space, C is the capacitance of the capacitor, A is the area, and D is the distance. So we have gotten another formula for the capacitance of a parallel plate capacitor. So this is an example. We want to solve this question. Calculate the capacitance of an empty parallel plate capacitor with metal plates with an area of what? 1 meter square separated by what? 1 millimeter. We have to convert this to meter, and that is 1 times 10 to the power minus 3. So having this formula now, can we get our answer? Yes. Epsilon naught is a constant, and the value is 8.85 times 10 raised to the power minus 12. So putting in all the parameters we have our area to be 1 meter square, we have our distance to be what? 1 times 10 raised to the power minus 3 meter, and putting that, so we have this to be this, we have our area to be 1, we have our distance to be 1 times 10 to the power minus 3. Putting this and multiplying it, we have this. And you remember that when we're talking about the unit for capacitance, we told you that 10 times 10 to the minus 9 is nanofarad. So this is 8.85 times 10 to the power minus 9 farad, and this can be represented as nanofarad. So you just have 8.85 nanofarad. So factors affecting capacitance, the factor affecting the ability of a capacitor to store charges, the factors affecting them. Number 1 is a dielectric medium. The effect of dielectric on capacitance is that the greater the permittivity of the dielectric, the greater the capacitance. Likewise, lesser permittivity of the dielectric, the lesser is capacitance. Some materials offer less opposition to the fluid flux for a given amount of field force. Materials with greater permittivity allow more field flux, hence greater charge is collected. So the dielectric medium has a great effect on determining the amount of charge that the capacitor will be able to store. The second is the plate placing. You know, we've talked about this, we already explained this. I told you that the first one is telling us that the type of dielectric material we use affects it. The type of dielectric material tells us the amount of charge the capacitor can store. The ability of the capacitor depends on the dielectric material. Another one is the spacing. The spacing, you know, I said that capacitance of the capacitor is inversely proportional to the what? To the distance, to the plates, to the separation between the two plates. It is inversely proportional. So big separation, small capacitance. Small separation, big capacitance. The last is what? The area of the plate. The effect of the area of the plate is that the capacitance is directly proportional to the area. The capacitance is directly proportional to the area. The larger the plate area, the more capacitance value, and this is it. Directly proportional and inversely what? Proportional. I know that we know how to do this, so let's go to the next slide. So now we have the parallel arrangement of capacitors. Just the same way we talked about the arrangement of resistors, we have also the arrangement of capacitors, just as we did for resistors. But the only difference is that the way parallel capacitor works is the way series is the way series resistors work, and vice versa. So the total, this one now is capacitors are connected in parallel. They are connected in parallel. You can see the parallel, this thing. They are connected in parallel. The total capacitance of the capacitors connected in parallel is just their addition. You know, recall that for resistors, this was the series, what's it called? This was the series connection. When we wanted to calculate the total resistance, that's when we use addition. That's when we use addition. So, but for the capacitor, it is the parallel arrangement that we add together. So you're just going to C1 plus C2 plus Cn and so on and so forth. Also, the series arrangement is like the parallel arrangement in the resistors. So the total capacitance of the capacitors connected in series are 1 over C1 plus 1 over C2, as we can see from this place. So energy stored in a capacitor. So we have that E is equals to 1 over 2 QV. 1 over 2 QV. So let's go to our board to derive it up to this point. 1 over 2 QV. 1 over 2 QV. So we have that our E is equals to 1 over 2 QV. And don't forget, this Q has a value. Recall that your C is equals to what? Q over what? Over V. And if you cross multiply, you can have that your what? Your Q will be equal to what? CV. So putting this, so we have that our E is equals to 1 over 2 what? Q what? V. So putting this in this equation, so E will be equals to what? 1 over 2. What is our Q? That's CV, right? Multiplied by the V that was there before, multiplied by this V. So E can also be what? 1 over 2 CV what? Square. CV square. Also, our V can also be what? V can be Q over C, right? So let's put that into this equation. We have that our E will be equal to what? 1 over 2 C, right? Then V, which is now square, will be what? Q over Q square, right? Over what? Over C square. So if 1C cancels 1C, our E will be equal to what? 1 over 2. We still have our Q square, right? Over what? Over C. And these are the formula for the energy stored in a capacitor. Energy stored in a capacitor. So that's how to get all the formulas. So example, two capacitors of capacitance 5 microfarad and 3 microfarad are connected in series, and the resulting combination is connected across 600 volts. 1 What is the equivalent capacitance of the combination? And 2, the total charge on the combination. You don't forget that we've already agreed that when capacitors are connected in series, to solve the equivalent capacitance, it's just the inverse addition, that is 1 over C1 plus what? 1 over C2. 1 over C1 plus 1 over C2, and we have 3 and we have 5. So let's go to our board to quickly do that. Let's delete the board. Okay, so we already have it that 1 over C total is equals to 1 over C1 plus what? 1 over C2. So 1 over C total is equals to 1 over 5 plus 1 over 3. So what are we going to have? We're going to have 15. So that will be 5, right? So 3 plus 5. So 1 over C total is equals to 8 over 15. But we don't stop here, because we're not looking for 1 over C total. We're looking for our CT, and our CT will now be equal to what? 15 over what? Over 8. So we have gotten our C total. So what else were we asked to look for? What else were we asked to look for? We were asked to look for what? The total charge on the combination. The total charge on the combination. Don't forget Q is equals to CV. Don't forget Q is equals to CV. And so we can do our normal multiplication. We've gotten this. When we did our division with the microfarad, we got this times 10. Oh, sorry, this is times 10 power minus 6 here. So putting that into this equation, we have our Q to be equal to what? CV. So whatever we got, which was what? 15 over 8 microfarad multiplied by our V, which is what? 600, will give us our what? Our charge Q. And that was what we did. That was what we did here when we said what? Q is equals to CV. Our C was what we got here, and it was 1.87 times 10 raised to power minus 6 farad multiplied by the V, which was 600, and we got this as the charge, which is in column. Let's go to the next question. A capacitor of capacitance 5 microfarad is subjected to a potential difference of what? 1000 volts across its terminal. Calculate the energy stored in the capacitor. So we have to check the formula we are given. We were given the capacitor of a capacitance. We were given the volts. So what is the normal formula to use to find the energy, like all the work done? So the W, which is this, is 1 over 2 CV square. I'm sure we derived all this formula in the previous slide. 1 over 2 C. And what was our C? 5 times 10 raised to power minus 6, because this is microfarad. Then multiplied by the volt, which is what? 1000 volt across its terminal. And we're able to get this, and we're able to get this. We had 1000, but 1000 square was what we wanted to use, because the V is squared. That's why we have it as 10 raised to power 6 here. And when we do our normal calculations, we are going to get what? 2.5 joules. We're going to get 2.5 joules. What are the uses of a capacitor? The capacitor have both electrical and electronic applications. They are used for several things, such as filters, energy storage system, engine starters, signal processing devices, etc. Capacitors are used for storing energy, which can be used by the device for temporary power outages whenever they need additional power. Capacitors are used for blocking DC current after getting fully charged, and yet allow the AC current to pass through the circuit of a circuit. Capacitors are used as sensor for several things, like measuring humidity, fuel levels, mechanical strain, etc. Capacitors can also be used in a time-dependent circuit. This could be connected to any LED or loudspeaker system, and it's likely that any flashing light or regular beeping uses a timing capacitor. And this is your assignment. So you can see this now. These two, you check, are they connected in series? Yes, these ones are connected in parallel. Then you are going to resolve it, and this one which is connected in series too, you have to resolve this first and change it to series before you can come and solve this. You know, in parallel you just add, and in series what do? You find the inverse 1 over of this. So the same thing goes to this place. You would find the equivalent capacitance and solve it, and also for this one. So the assignment. So thank you for being in this class. See you in the next class.